Welcome back everyone. In this video we're going to talk about JVM bytecode instructions. So I'm going to go through all the 200 or so instructions and we'll see what you can do with JVM bytecode. So last time I gave this example of this simple method here and how it decompiled to bytecode instructions. I'm not going to go through it again, but you can see it looked like this. So we had a constant pool to store constant data. This was the bytecode for the constructor, which is generated automatically, and the bytecode for method. So the first thing we need to talk about is the execution model. In particular, I want to tell you about where the data that we're going to be manipulated is stored. And it's stored in a couple locations. So the first of these locations are locals. And locals are used for parameters, so the function parameters, and local variables that you declare inside functions. Then there's the stack, and the stack is where we're gonna put data that we're actually manipulating. So every bytecode instruction is going to get its data mostly from the stack. It's going to take them from the stack, and it might also push a result on the stack. Another location where we can store data is with an object, right? You know, in Java you can have objects, they can have fields, while you can store data in fields. And there's also static fields, which are class specific instead of being object specific. And all of these can be pushed onto the stack where they can be manipulated, and then you can take something that's on the stack and put it back in a field, for instance. For methods, so any kind of code that we're going to run is going to be within a method. And there are two kinds of methods: static method, again class specific, and virtual methods, for which you need an object. You know, there needs to be a this value. The big difference between static methods and virtual methods is that static method, you don't need to look up the method that you're going to call. Okay, you always know what code you're going to execute. Whereas virtual method, there could be a subclass that is going to override the method. So there's multiple implementation for the same method. And when you're calling the method, you need to take the object, the this, and look at actually which class it is and which implementation you need to call. So the JVM deals with 32-bit values, and this means a couple of things. It means that long and double values, they are 64 bits, and so they occupy 2 slots. I will show you here. You see there's the size of the stack, the maximum size of the stack, which is 1. Well, if you have a long there, it counts for 2. Another consequence is that if you're dealing with short and byte values, so like integers that are smaller than 32 bits, they are extended to 32 bits in order to operate on them. We already talked about the constant pool. The constant pool includes a lot of string, including string literals used in programs, class names, field names, method names, and also type descriptors. So there's this special notation that describes the type of method with letters. So like the capital V was for void, capital I was for integers, etc. We will talk about this notation a bit later. Big integer and big floating point numbers also live in the constant pool. Those that don't live there are small integers. So for instance, in the example from last time, we showed that we returned the integer 42. 42 is a small integer, and so we can actually encode that in the instruction directly. I will explain that. And finally, you can also have dynamically computed constant. This is a new feature of the JVM, it's not very important. It enables some interesting optimizations, basically. So, what's in a JVM instructions? A JVM instruction has 2 parts. One is the opcode, which is what identifies the instruction. The opcode is encoded in 1 byte, which means that there is maximum 256 instructions possible. Okay, and like I told you, Java has about 200. And we'll see that they selected these instructions depending on the available space. So if they had more space, they would have put more instructions. Now, if it was really necessary, we could do variable length opcode. We could say the opcode 255 is the opcode for variable length, and then we are going to read the next byte, and that byte is going to give us 266 more instructions. But currently they don't do that. And the instruction set is very stable. So far they've only added a few, I think maybe 1 or 2 opcodes since the start of the JVM. Now, Instructions also have operands, sort of parameters. Most of the time, these operands is going to be a reference to the constant pool. So the index in the constant pool for some value to manipulate. Sometimes it's going to be an offset in the bytecode. That's for jump, like a go-to statement that say go to this instruction. And sometimes, but rarely, it's going to be immediate value. So I told you about the example where we return 42. Well, in that instruction, 42 is an operand. It's encoded in the operand. So these values are, the maximum size for them is 16 bytes, so it's 2 bytes. So that corresponds to a short in Java. Anything bigger, you need to put it in a constant pool. And with that, we can actually get started and review our instructions, all 200 of them. So the first type of instruction I'm going to talk about is load instructions and store instruction. A load instruction pushes a variable on the stack. A store instruction stores a value from the stack, from the top of the stack, into a variable. There are 50 instructions of that type, okay? So there are load instructions and there are store instructions. Then there are a bunch of variants depending on the type. A is for objects, okay? And A actually means address, that's why it's A. F is float, D is double, I is integer, and L is long. This is a pattern that will repeat many times as we see instructions. And then we also have a specific variant, so 0, 1, 2, 3. Those say, well, load from variable 0, from variable 1, 2, 3, store into variable 0, 1, 2, 3. And you notice that I use a bracket here, and this means that this part is optional. So there's also a version of these instructions that does not have this suffix. Okay, and in that case, then you need to specify the variable index as an operand, because of course there might be more than just 4 variables. So an example of such an expression is a load. So this loads an object from a variable into the stack. Another example is I store 0. So this stores an integer from the stack into variable 0. So when you take into account all the variants, there are 50 instructions because there are 5 types here, times 2 variants here, times 4, plus 1 for the one where you have to specify the variable number in the operand. So that's 5. So 5 times 2 times 5, that's 50. Alright, so that's load and store to transfer between variables and the stack. Now there are some more peculiarities, and these are not super important, but let's mention them briefly. So there is INC, which basically takes as parameter 2 bytes and interprets that as a short, and it adds that value to an integer variable. The reason is that incrementing an integer variable is very, very common. That's what you do in for loops all the time, and so they provided a specialized instruction to do that. Another one, and this one is a bit special, is wide. So wide is a modifier that you put in front of a load or a store or a INC to access a wider range of local variables. Because by default, you only have 1 byte that's used to index the list of variables. Okay, and so that gives you only 256 variables. Normally that's enough, your method is not that big, 256 variables should be plenty. But in case that's not the case, you can use the wide instruction, and then you just, after that, you put the normal instructions, so you put wide, a store, then you encode the variable index on 3 bytes instead of just 1. So the reason why they did this is to preserve opcode space. So instead of taking all these 50 instructions and then making a wide version of them, that would have made 50 more instructions. That's just 50 instructions wasted. So instead they just add 1 opcode to do all of this. Okay, so it's a bit like the variable length scheme I was talking about. So what we need to talk about is preserving opcode space. Because one question you might have, why do we have these specialized 0, 1, 2, 3 opcodes? Why not just always use the generic version? Well, the reason is that when you use those, it takes 1 less byte to encode. This is part of the opcode. There's 1 opcode, 1 number in the opcode space for each of these instructions. So it only takes 1 byte, and that's it. You don't need anything else. Whereas if you take this one, now you need 1 byte for the instruction, and you also need 1 byte to encode the index. And that's also why you only have 1 byte and not 3 by default, because if you had 3 by default, then each time you use this instruction, you would need to put the opcode and then put 3 bytes. And that increases the size of the bytecode that you generate. And basically, a smaller bytecode is going to be faster to execute because there's less input-output, so there's less to read. And there's going to be less wasting of cache space. So the memory access is going to be faster. You can use the cache more efficiently. So basically, a smaller code size is typically beneficial. And that is true with bytecode, but it's also true with machine code. And often, there's even the case that optimization can be detrimental. When you optimize too much, and it makes the code way bigger than it used to be, what you win in terms of efficiency from this new code can be lost because the code size is now much, much bigger and you don't use the caches efficiently. So that's something to keep in mind. And so what you should remember here is that the reason why we have all these shortcuts is to save space. Okay. And since the designer of Java had a space of 256 for instructions, they said, well, we don't need to save that space. We have space available, so we'll encode the most common instructions directly in the opcode instead of requiring more parameters for them. So the next instruction that we're going to see are instructions that push constant onto the stack. And there are 20 of those. We can push no onto the stack. We can push -1, 0 to 5. We can push for floats 0, 1, 2. For longs or doubles 0 or 1. Then there's these instructions, which are the most interesting. So LDC will take as an immediate parameter a constant pool reference, and it will load that constant. LDC W, and W is for wide, will also take a constant pool reference, but LDC takes only 1 byte for reference, so you can index from 0 to 255, whereas the wide version will take 2 bytes, so you can index potentially up to 65,000 constant pool entries. The LDC to wide is the same as the LDC wide, but it will let you get 2 30-bit values, and so basically can be used to get longs or double from the constant pool. Then you have bpush and cpush, and these let you push a byte as an immediate value or a short as an immediate value, so that you do not have to look up in the constant pool. So again, why are there so many instructions when in theory you could do everything with LDC wide and LDC2 wide? Well, same reason as before, this helps keep the bytecode short by giving their own bytecode to instructions that are used often. So another type of instruction that we have is type conversions. Java does implicit type conversions. For instance, if you type 1 plus 2L, 1 is going to be integer and 2L is a long. And what Java does in this case is that it implicitly converts the integer into a long. This does not happen in the JVM, and so you need to insert these type conversion instructions explicitly. So they're very simple. They just take a value of the stack, they pop it off, and they push the converted value. So you have all of these. So for instance, you would have I to D, which convert an integer to a double. You do not have the identity pair, so I to I does not exist, of course. Then you have these, and these truncate integers. So you have I to B, for instance, and that truncates integer to a byte. I said before that the JVM only works with 32-bit values, and that's still true. So what this does really is not diminish the size of integers. It will truncate the integer by nulling the bits that cannot be used. So for instance, you have a big integer and you want to cast it to a byte with I to B. A byte only takes 8 bits, and so what it will do is that it will null the 24-bit of higher order, and it will only leave the 8 low-order bits untouched. We have instructions, of course, for arithmetic operations and binary operations. So these pop 2 values of the stack and they push the result of the operation on the stack. So we have addition, division, multiplication, subtraction, negation, so that's binary negation, and the remainder of the division. For integer and long only, we also have binary AND, binary OR, shift left, shift right, unsigned shift right, and exclusive OR. We'll get to an important family of instructions, and these are instructions that manipulate the stack. First of all, we have the dup family. So dup duplicates a value. So we'll take a value on top of the stack and it will push a copy of that. Then you have dup2. and this duplicates two values or a double-sized value. So that's what you would use to duplicate a long or a double. Then you can also add these x1 and x2. The best way to think about them is that dup does not actually push a new value in the stack, but inserts it above the top value. Okay, so it does not push, it inserts it above the top value. If you take that meaning, then what x1 means is skip 1, okay? So you have value 2, value 1 in the stack, and by the way, the top of the stack is here. What you would normally do is have value 1, but instead you're going to skip a value. So instead of insert it here, you're going to skip it and insert it here. So that's the one you insert. So you go from value 2, value 1, which is the top of the stack here, to value 1, value 2, value 1, which is the top of the stack here. x2, what it does is that it skips two value, okay? So if you have value 3, value 2, value 1, top of the stack here, so what you do is that you will skip two values, and then you will insert the duplicate. You can combine x1 and x2 with dup2, and then what we'll do is that you have to imagine that here, each time we write value 1, we write value 1, 1 and value 1, 2. Okay, then it's exactly the same, instead of having a single value of two values that move around. Then we have pop. Pop removes the value from the top of the stack, and pop2 removes two value, or a double long value. And you can do nothing with that, it just removes it. And finally you have swap, and swap just inverts the two values at the top of the stack. You'll notice that there's no swap2 instruction. So here's a question for you. Imagine that you have two longs on the top of the stack. How do you swap them? I'm not going to answer, but you can probably Google the solution if you're stuck. I'm going to give you a hint. You only need the instructions on this slide. Moving on, we're going to talk about arrays. So just like for variable, we have load and store instructions. We want to load and store from and to arrays that are of a certain type. So objects, A for address, float, double, int, long, char, byte, and short. So you may notice that unlike before, now we have these char, byte, and short, and that's because the representation of an array of bytes is an array where each byte is stored actually in one byte, not in one integer. Same for short. Each short is stored in a short, which is 2 bytes. So if you take the load instruction, what it takes is it takes an array reference from the stack, an index from the stack, and the top of the stack again is here, removes them, and then it pushes the value that it read from the array on the stack. Store is the opposite, so it also takes an array reference and index, then it takes a value, and it removes all of that, and it writes the value into the array. So something interesting to note is that BA load, it's used for bytes indeed, but it's also used for booleans. So the way Java represents an array of booleans is actually as an array of bytes. Each boolean gets stored in 1 byte. Why do they do it like that? Why not store boolean as bits? Because you just need a bit, right, to represent a boolean, true or false. My best guess is that they're okay with taking more memory, and remember that using more memory is not great because you waste the cache. But they're okay with doing that because it saves them instruction from extracting the boolean value from the byte. In current architectures, the memory is addressable byte by byte. So accessing a byte is very fast. But if you represent a boolean as a bit, now each byte that you are going to read is going to have 8 booleans. And so what you need to do is apply some kind of mask to retrieve only the bit that you're interested in. And that takes a few operations. And so I think they made the calculation that it will be more economical to not do that and to instead waste some memory. Then we have 3 instructions to create new arrays. So a new array creates an array of primitive, and a new array creates an array of object. In both cases, they take a constant pool reference, which is going to hold a type descriptor or a class object for the component type of the array. They also read the size of the array from the stack, and they will push the array on the stack. So multi-A new array is to create multi-dimensional array of objects. Remember, the A is for objects. The way it works is that it takes a type, a constant pool reference as parameter, and that's the type of the component. So that's always an object type, a class, and the number of dimensions of the array. Then on the stack, you need to put as many sizes, count, as there are dimensions. So if you're going to create a two-dimensional array, you need to put 2 counts. If you create a three-dimensional array, 3 counts, etc. It removes all of that from the stack and it will push the created array. Now you might have a question, why don't I have a multi-new array? Why is it always multi-A array, which is for objects? The answer is that when you want to create a two-dimensional array of integers in Java, you do not create a big array of integers that you access as though it was a multi-dimensional array. Instead, you will create an array whose components are a pointer to array of integers. And actually, if you want to create a two-dimensional array of integers, you are not going to use that at all. Instead, what you will do is that you use a new array to create an array of integers. And once you've created this outer array, you will fill it with array of integers that you create using new array. Now, if you want to create a three-dimensional array of integers, then you will use multi-ANuArray with 2 dimensions. And then you will fill the last dimension with array of integers that you create with new array. Finally, you have array length. So that's very simple. It takes the array from the stack, removes it, pushes the length of the array on the stack. Next up, we have field access. GetField and PutField take a field reference as an immediate argument, which is itself made of a class, the field name, and the field descriptor. The field descriptor is the special notation that describes the type. GetField takes an object off the stack and pushes the field value there. PutField takes an object from the stack and a value, also from the stack, and sets that value, leaving the stack empty. We also have getStack and PutStatic, which are the same, but for static fields, so no object reference are actually required there. Remember earlier we saw arithmetic and logical binary operation? What we did not see there were comparison operators. The JVM authors could have decided to make comparison operators similar to arithmetic operators, but they didn't. And again, I think this is to save instruction set space. You have to implement equal, not equal, greater, greater equal, lower, lower equal. So 6 instructions times 3 for integers, long, floats, and double, actually times 4. Also on some architectures, and notably that's the case on Intel architectures, this comparison is a single machine instruction that works the same as the instruction here in Java. So how did they implement it? First of all, they separated integers from the other 3 types, saying that integer comparisons are much more common, and when you do such a comparison, it's typically combined with a control flow jump. So it's going to be used in an if statement or in a while statement, for instance. We'll see those on the next slide. For the 3 other kinds, so that's long, double, and float, there's a single instruction for comparison per type. So let's take double and float as an example. So the instruction for instance is going to be called dCMPG. The CMP part is in common. D and F is for double and float, and G and L I'm going to explain in a short while. Here, A and B are 2 operands taken from the operand stack. And if A is bigger than B, then the instruction will push 1 on the stack. If E is smaller than B, then it will push -1, and if they're the same, it will push 0. Now we explain G and L. So basically, this comes from the fact that double and float, they can also be NaN, none, not a number. Okay, and if either of A or B is not a number, then we need to decide what to push on the stack. If the instruction ends with G, then we'll push 1 if we encounter not a number. If it's L, we'll push -1, and L is for lower and G is for greater. For LCMP, it works exactly the same, although of course there is no G or L suffix in that case. Instance of then, it takes a class reference as an immediate parameter and an object from the stack. It pushes 1 if the object is an instance of the class that's being referred, and 0 otherwise. CheckCast does the same as instance of, but it throws an exception if the object is not an instance. As the name implies, it's used for checking that casts are safe. And it's not really a comparison, but I put it here because it does the same as instance of. Now we come to jump and conditional. So jumping simply means jumping to an instruction ahead or jumping back to a previous instruction. The jump is expressed by an offset, which is usually encoded on 2 bytes. It can also be encoded in 4 bytes for the go to W instruction, and W there is for wide. So goto is the unconditional jump. So for instance, if the offset for goto is 10, then you'll unconditionally jump 10 instructions forward. So why do we have the wide version? Well, 2 bytes lets you jump 32,000 instructions forward and back, which is a lot. But it might not be enough for really big methods. If your method is a couple thousand lines of code, that might not be enough actually. The wide version also lets you write code where functions are not encoded as JVM methods, but as jumps in the instruction stream. And that's actually the way it works with most machine code on most architecture. For instance, if you have a C compiler that emits machine code, the way you'll call a function is that you'll set the stack and the register up in a certain way, and the certain way is called the calling conventions. There are a few popular calling conventions. For instance, they will say that all the arguments of the method have to be in the stack, and the return value will be put in the EAX register. That's just an example. So you will set up the stack and the registers, and then you will jump to the address of the function. Okay, and so using goto wide, you can do that in the JVM, although it's not recommended. So next we have an instruction that is for object comparison. And this is identity comparison, so basically comparing the object pointers, seeing that really we have the same object, not just objects that are similar as per object equals in Java, but really the same object. So what this does is that this jumps, in the case of EQ, if the objects are the same. Otherwise, so if they're not the same, it's going to execute the next instruction. And it's the opposite for NE, for not equal. So if they're not equal, it's going to jump. Otherwise, it's going to execute the next instruction. So this takes 2 stack operands, which we compare to see if they're equal. Here we have exactly the same thing, but for integers. So that's dependent of the double, long, and float comparison that we saw in the previous slide, but here we also do the jump. And so we have a equal, not equal, greater than, lower equal, lower than. Then there is this, which takes a single stack operand. And what this does is that if equal here, then if the operand is 0, it will jump. Not equal, if it's not 0, greater or equal, if it's greater or equal to 0, etc. And these are exactly the results that you would get from the CMP operation here. So they are to be used in combination. And finally, you have if null and if non-null that also takes a single stack operand and will jump if it's null or if it's not null. Object creation. So object creation is very simple. There's an instruction called new, and this instruction takes an immediate parameter, which is a class reference. So what new does is that it simply allocates memory for the object, but does not call the constructor. So what do you need to do to call the constructor? You have to use this instruction called invokeSpecial, and we're going to talk about invokeSpecial in a few slides. But use the invokeSpecial to call a method called init. Okay, and in this case, the angle brackets here, they are part of the name. Okay, they're not a notation. And you'll remember that init is the special name that the JVM gives to constructors. Interestingly, when you load bytecode into the Java virtual machine, it will run verifications on the bytecode. And this will check that after you create a new object with new, that a constructor is called on it. And if that's not the case, it will reject the bytecode unless you disable the verifications. Next up, we have method invocation. So first of all, the JVM refers to methods by their name. So to invoke a method, you need to know the full name of the class in which it's defined and the method name. And those things can be stored in the constant pool. In fact, all method invocation instructions have such a reference as immediate parameter. There are 5 kinds of invocation instructions. The first of which is invoke static. So it is used to invoke static methods, and because these are static, there is no need for an object of that class to be on the stack. For invoke static, you always know exactly which code you're going to call, because you give it the exact class where that's defined. Next up, there's invoke virtual, and that's used for your regular virtual calls, which use dynamic dispatch. The usual way this lookup works is that each class records all of the methods that can be called in it in a method table. And if you know C++, in C++ they call this table a vtable for a virtual table. So this table includes the method defined in superclasses as well, even if they are not overridden. This means that once we get the class of the object, we can immediately look up the implementation of the table in that table. Note that we do not know which implementation will be used at compile time. For instance, the object might be typed as a Java long object, and we're going to call the toString method in it. Well, a different method will be called if the object is a string or if it's a list. There is no way to know until the code is run, and it might even be different each time the code is run. Next, invoke interface is the same as invoke virtual. The difference here is that the lookup is a bit more difficult and it's also a bit more costly because you can only inherit from one superclass in Java, but you can implement multiple interfaces, and that does make the lookup more difficult. Then we have invoke special, and invoke special as static linking, meaning that just like invoke static, you always know exactly the code that you're going to invoke. But these are not static methods, and so you do need an object to act on. And there are three examples of cases where you need invoke special, and those are private methods, constructor calls, and super method. So for private methods, those cannot be overridden, so you always look in the same class for those. For constructor, that's easy because if you do like new object, you always know which class to look in. And you also have super constructor, but then you just need to look in the superclass and you know what that is. Super method is a bit more trickier to understand. You might think that for super methods, you will need something like virtual calls. And the answer is no. No, you don't need that. And that's because when you call a super method, the compiler knows the exact type of the current object, of the this object. And it knows that statically. And because it knows that, it can find the first ancestor class, so the superclass or the superclass of the superclass, that implements the same method. All that information is available at compile time. So the key difference here is that really we do know the type of the this object. We do know the real class for it. Whereas in invoke virtual, we do not know the class of the object until runtime. And finally, we have InvokeDynamic, and this one is a bit more special, and it's on the next slide. So if you're interested in Java, you might have heard about InvokeDynamic. And basically, what's being said is typically, the InvokeDynamic is great to implement dynamic languages. And typically, there's not even an explanation for that. And here I'm going to give you an explanation of why it's so useful. So what InvokeDynamic does is that it's basically a wormhole instruction. The first time you use InvokeDynamic, it will go to a bootstrap method. And this method is a normal Java method that returns a call site. And you have to write this method yourself, so it's not something that Java provides, you have to write it yourself. And this is a normal Java object, but that gives information to the JVM that will use it. After the bootstrap method is called, and this happens only once, the instruction is patched, meaning that the next time you call this instruction, it will not go to the bootstrap method, but it will go to the call site directly. And so this object, the call site, it refers to some method or some code at least. The point here is that this can be optimized just like a regular call. And so what this allows you to do is to not decide at compilation time what you're going to call, but to wait until runtime to do that. And in particular, what's really, really interesting is that if you save this call site object, then you can use it to change the target method. So change the destination of the wormhole. And changing the destination is useful to write something called polymorphic inline caches. This will probably be explained in the invited talk by Christian Hummer on truffle. And we might speak about it also in the optimization lecture, so I don't want to talk about it too much here. But basically, we can always use a method that is tailored to the types that we've actually seen, and a condition to see that the new value is a type that we've already seen. So what we need to know is that it's an instruction that allows changing the destination dynamically while enabling optimizations, and that's very useful for the implementation of dynamic languages. And like I said, we'll talk about it later in the course. Finally, we have a few more instructions, and those are the last one we'll see. So first of all, you have instruction for return, and return without a prefix is just returning from a void function. Otherwise, we have the usual type prefix or object close double integer long when you return such a value. You have an instruction to throw exceptions. You have an instruction to enter and exit a monitor. So a monitor is what's used when you use synchronized blocks in Java, for instance. It's a kind of mutex. You have the nup instruction that does nothing. And then you have the lookup switch, a table switch, and those are difficult, but they're used to optimize the switch statement in Java. And the switch statement, if you only have to know one thing about it, is that it's more efficient than chain of if and else, because basically it will attempt to directly jump to the right location instead of trying every possible alternative. So we come back to our example that we gave in the previous video. And those are very trivial examples, but I want to go over them again now that we've seen all the instructions. For the constructor, the first instruction loads the local 0. Oh, and by the way, I've been saying before variable a lot, but really the right term is local, because local can map to a variable, but it can also map to a function parameter, for instance. You load the local 0 onto the stack, then use invoke special to call a constructor. So this is already a constructor for the class main, and we will call the super constructor from class java object. And this is a constant pool reference. And then we return. Constructors do not actually return values. They are more like initialization methods. So you'll remember that to create an instance, we use new, and then we call this constructor initializer. Okay, next on we have foo. The first instruction of foo is get static with a reference here to system.out. Then we use LDC to load a constant, and the constant is this constant pool reference that is the hello world string. So now we have system.out and hello world on the stack. Then we use invoke virtual to invoke the println method. Okay, so the first item on the stack will be the this pointer, system.out, and then the second one will be the parameter, hello world. So these get taken off the stack, and we will print hello world to the console. Next, use bypush to push the integer 42. So notice that this is an immediate parameter. It's not a constant pool reference because it's a small integer. And then we use iReturn to return this integer. Before I let you go, there are a few more topics that I want to comment on. And the first one is register allocation. Many lower level instructions that we've seen, they map straightforwardly to underlying machine code, so like Intel machine code. However, most CPU architecture use registers. Registers are explicit, and that's in opposition with the caches that exist in the memory hierarchy. So when you access memory, it could be in the main memory in RAM, or it could be in a layer 2 cache, or in a layer 1 cache. And the layer 1 cache is faster than a layer 2 cache, but it's smaller. And this caching happens automatically. So when you access something in the memory, it'll be cached in the layer 2 cache and in the layer 1 cache. That's not so for registers. You need to assign them explicitly. Registers are also faster than the layer 1 cache. So if you were to map the JVM stack to the memory, it could only go as fast as the layer 1 cache and not as fast as registers. And anyway, this wouldn't work because most machine code instructions need to work with registers. They will change specific registers. So how do we decide which data goes into which registers? And the number of registers is also very limited. That's something important. For that, we need to use a register allocation algorithm. We don't have the time to talk about them, and typically you don't really need to know about them because you'll use some component that does it for you. But if you're interested, you can go to this website, and this will give you an example of how it works, and it will give you an example using a real Java program and seeing how that leads to register allocation when it becomes JIT compiled. Another topic I want to talk about are the differences between the JVM platform and the Java language. So the JVM was obviously made for Java. So in terms of feature, they map fairly well, but there are a couple key differences, two in particular. The first one is that there's no generic type in the JVM. Generic types mostly exist in the semantic analysis part of the compiler. If you have something typed like a list of type T, there's no way to get the type T using bytecode. The information just does not exist, which is to say that generic types are not reified. There are no objects for it. Now, this is not a fundamental limitation. For instance, C#, which is a language that is very similar to Java, does have reified generics. You could also use the JVM to implement a language with reified generics. There just isn't any special instruction support for it in the JVM. And that's significant because JVM does have a notion of type, right? We have an instance self-instruction, there is a checkcast instruction, so JVM is aware of type, but will never be aware of generic types. That's something you need to code in yourself. Another difference is that there are no checked exceptions in the JVM. In Java, checked exceptions are those where you have to declare them in the function signature or you have to add a try-catch around them. There's no such restrictions in the JVM, so all exceptions act like the Java runtime exception. So once again, this is just a check that Java does in the semantic analysis part. So there are a few differences, but these are the two main ones. The final thing I want to talk to you about is how to get code into a Java virtual machine. So classes are loaded into JVM when they are required, and they are required when they're being referred to for the first time. And the JVM will use the name of the class to locate it, so either it's already loaded or it needs to load the class from its class file. And then it will use this name, the name of the class, to locate it in the class path. So the class path is something you might have played with when you install Java or something like that. It's basically the directory or the directories or the jar files in which Java is going to look for the class files. After the class file is loaded, the bytecode is going to be verified. And there are a number of miscellaneous verifications. So we said before that when we use the new instruction to allocate an object, the JVM will verify that a constructor is called in that object. It will also verify that final variables are not rewritten after a constructor was called, and a couple other things like that. There is a very important class of verification which has to do with something called the type state. What the verification does is that it makes sure that any instruction reachable through multiple paths must be reached with the stack in the same state. So the stack must have the same size, and every item of the stack must have the same type, no matter the path that we used to reach. So what do I mean by reachable through multiple paths? Well, an example is if you have an if-else instruction, then the first instruction after the if-else is reachable through multiple paths, because you can either go through the if part of the if-else, or you can go through the else part of the if-else. And so, for instance, if in the if part, we push a value in the stack, but we don't do so in the else part, then we have a type state violation on the instruction after the if-else. Because through one path, there is one more value on the stack, and through the other part, this value is absent, and so the type state is not the same. Knowing this type state for every instruction leads to some very nice properties. So it means that Java knows the type of every local and every slot on the stack at any given time. This is very different from machine code, where values are basically integers and you're free to interpret these integers any way you want. They could be integers, they could be characters, they could be addresses. It also means that it's not possible to iterate an array to copy it on the stack. Why is that, do you think? Well, it's because the type state would be different depending on the size of the array. Another property that is enforced is that the stack can't overflow if you don't recurse. So if you do infinite recursion, it's still possible to overflow the stack, but it will never happen inside the method. So in conclusion, we've seen that the JVM performs stack-based computation. It stores data on the stack, of course, but also in locals that are in methods, in the constant pool, and in object fields. It comes with a built-in garbage collector, which most of the time is great, but it means that you have no fine-grained control over memory location, of course. It also comes with a built-in just-in-time compiler, which can make your code fast. The JVM Bytecode instruction set has low-level stack operation to manipulate the stack, to do additions and things like that, jumps, and also transfer between stacks and the locals, the fields, the constant pool. So those are your load and store instructions. And then it has a set of highly abstracted instructions, and particularly there's instructions to invoke methods. There are a few other things that are more abstract. For instance, there's exception handling. And by the way, we haven't talked about how try-catch was implemented. And that's because it's not implemented with instruction, but by specifying something called an exception table. But this video is really long enough, so we don't have time to talk about that. The goal of this video was not to make you a JVM guru, Although if you watched this video and the previous one, you're probably pretty well informed by now. The goal was to give you a feel for what an instruction set might look like and what sorts of consideration guide the design of the instruction set. And crucially, also how these instructions relate to a real programming language. We focused on the JVM Bytecode instruction set not because it's the most interesting or the most general, but because it's simple enough that I can give a full tour of it. And it's also an excellent tool to use to implement your own language. Like I said at the start, the JVM offers an excellent trade-off between effort invested and all the value you get from using it. We can take things one step further by actually generating some bytecode. So no matter how much you learn from presentations such as this one, getting your hands dirty really has a tendency to make things click. And so I will show you how to generate bytecode in the next video, using a library called ASM. So I'll see you next time. Until then, take care, be excellent to each other.